Here we're told we have an air compressor operating at steady state with air entering at given pressure and temperature, and then it goes through a polytropic process and exits with a given pressure and temperature. So let's go ahead and sketch this out. So let's say this is our compressor. Here's the shaft driving the compressor, and the air comes in here, call that state 1, and it's going out here, call that state 2. And we're given the information, by the way, the units here, this is pounds per square foot absolute. And this, of course, is degrees Fahrenheit, right? So we're given English units here. So we're told it's a polytropic process, which means that the pressure times specific volume raised to a constant n, that constant n is just for the specific volume, that's equal to a constant. So I'm going through this compressor from 1 to 2. This is how the pressure and volume are related. So we're asked to find the exponent for the polytropic process, so we need to figure out what that n is and then sketch that process on a PV diagram. So to find what the constant n is, we can make use of the given state information at states 1 and 2. Now we know the pressure, right, that's given, but we're not given the specific volume, but we can find that because we're told that the air, that we're dealing with air, and we're going to assume the air is an ideal gas. That's almost always a good assumption. So from the ideal gas law, we know PV equals RT. So to find the specific volume, it'll just be the gas constant for air times the temperature divided by the pressure. So we know P1 and T1, so we know those values. And this gas constant for air, we can look that up in a table. And let's see if I've got that written down here. Yeah, so just so you have it, the gas constant for air in English units is 53.3533 pounds force feet times feet all over pounds mass times degrees Rankine. So unusual set of units, but it's just because it's the English system. So anyway, you can do that calculation here. You just have to be careful of unit conversions. But if you do that, you'll find that V1 comes out to be, let's see what the V1 is, 1850 cubic feet per pound mass. And V2, doing the same calculation, is 536 cubic feet per pound mass. Okay, so that's just using the ideal gas law to find those. And then we can use our polytropic process relation. So P1 V1 raised to the n is going to be P2 V2 raised to the n. Okay, so then let's do just a little rearranging of this. So we'll have V2 over V1 is equal to, let's see, P1 over P2 raised to the 1 over n. Just double check that that makes sense. Yeah, so we have that, and now to figure out what n is, if you take the natural log of both sides, what you'll get is the natural log of V2 over V1 is equal to 1 over n times the natural log of P1 over P2. So it kind of helps to know that little math trick, you know, and when you take an expression like this that has something raised to a power and you take the natural log of that, it'll become it'll be that power times the natural log of the thing in parentheses, so it looks like this. So then we'll have n is equal to the natural log of P1 over P2 all over the natural log of V2 over V1. Okay, so that's how you would find n, and if you do that calculation, you'll get that n comes out to be 1.30. Okay, so that's a way you can determine that value for n. So it's just making use of the polytropic process relation, the ideal gas law, and then this sort of a little math trick to convert it into natural logs so you can isolate out the n. All right, so the next part of the problem is to sketch the process on a PV diagram. So there's pressure, specific volume. The pressure increases as we go from state 1 to state 2. That's because we're dealing with a compressor. Compressors increase the pressure. And also, since it's being compressed, you'll see that the specific volume also decreases, right? It goes from 1850 to 536. So that means our state 1 is going to be over here. There's our V1 and our P1. State 2 will be somewhere here, P2 and V2. And then it's a polytropic process, so that means that PV, and here we found N was 1.3, is equal to a constant. So what that looks like, it's like the pressure varies like a constant over the specific volume to the 1.3. So that's pretty close to being a hyperbola. It's not quite a hyperbola, because if it was a exponent of 1, then it would be a perfect hyperbola, but it's pretty close. So it'll look something like that, just as a rough sketch. And we're going, of course, from state 1 to state 2. So that's it. That's part B. We've checked that off as well. All right, so we'll go ahead and end the example there.